Good evening, all. Fifth day of sixth day Adult Online FTP on Smart Energy Storage Technologies from Research to Real World Application. Today we have two sessions. One from Keltron, where India's largest capacitor manufacturer and who establishes the first commercial supercapacitor facility in India. And second session is by Dr. Sri Lakshmi MP, NIT Calicut. So today we have Mr. Sudheer AV and his team. And Mr. Sudheer AV is a technical consultant at Keltron Component Complex Limited and former head of Keltron Electronic Research and Development Center. He brings over 30 years of industrial R&D experience in passive components, material development, and large-scale manufacturing. He has led key projects such as supercapacitor production facility at Keltron, modernization of capacitor plants, and indigenous material development, resulting in significant cost savings and import substitution. He has also worked closely with national research laboratories like VSSC, CMET, and NMRL, and holds an Indian patent in ocean wave energy harvesting. So we are pleased to have Mr. Sudheer Ravi and his team as our today's resource person. So on behalf of FDP organizing team and GC, I welcome.
Good evening, sir. But there is some problem over here. There is a power interruption. We are trying to bring it back. Just a couple of minutes, sir. That's all.
Okay, okay.
Hello, am I audible?
Yes, sir. Yes, sir.
Yeah. First of all, I'd like to thank you, Government Engineering College, Kannur, to giving me this wonderful opportunity for this session regarding supercapacitor, and myself, Sudheer AV, Technical Consultant, Keltron Component Complex Limited. I was retired from the service as a head of R&D department, and now I was appointed by a GO supporting for some project work that has been continuing during my period itself. Today I am going to introduce you about the supercapacitor characteristics, advantage, some setbacks, brief material science, and manufacturing process, uh, comparison with battery, application with the supercapacitor, same some practical modeling of the energy harvesting system, and a brief description of our products as well as our manufacturing lines. So this is the situation. As per the situation, you know that we are living in an energy intensive world. For centuries, we had been heavily relying on fossil fuel to meet our energy demand. We know that the fossil fuel resources are draining out rapidly. Not only do that, they are also causing a lot of global warming issues. Now we are in a phase of transition from fossil fuel to this renewable energy as well as other form of energy. In that situation, the energy production, for example, in the case of um, uh, solar energy, it is available in the daytime, but the energy demand is mostly in nighttime. So the storage of energy is also one of the important uh, sector we have to address. And presently, as far as electrical energy is concerned, the main storage form is lithium battery or rechargeable batteries, as well as to a certain extent supercapacitor, where pulse power and high current requirement are needed. So before starting our session, I like to just focus on some conventional energy form and what are the challenges we face during the transition period from fossil fuel to this renewable energy or electrical energy sector. Now, the main thing is the fossil fuel are very compact. You know that 1 kg of, I'm not actually giving the numericals, just for an introduction before going detail into the supercapacitor. 1 kg of petrol can produce 42 megajoules. But you know that the energy conversion of all internal combustion engine is of the order of 30 to 50%. So we will only get the a portion of the energy. The rest of the energy is wasted to the environment. So it is not the carbon dioxide or carbon particle emitted from this engine is the issue. The energy, amount of energy it is wasted in the form of heat to the surrounding is also a big issue. So looking into the energy density, 1 liter of petrol can produce nearly 11 kilowatt of hour energy. But considering this efficiency, a petrol engine can only produce 3.3 kilowatt of hours of energy, whereas most modern lithium-ion battery can handle 350 watts hour per hours of energy per kg. I am speaking about the energy per kg. So even though this is a truth that the conventional whatever the most modern technology regarding the battery is very high compared to the chemical energy in the form of fossil chemical energy, mainly in the fossil fuel, it is not very near to it. But however, considering the efficiency of the system, because all the electrical motors, everything nowadays works at more than 90% efficiency. And the conversion efficiency of the battery as well as supercapacitor is very high, it is almost most often greater than 90%. So these sectors will grow definitely in the future and will gain strength. So that we can help the surrounding, we can reduce the wastage, and reduce the global warming, and everything. And also the fuels, fossil fuels are not going to last for a long. So we have to change it definitely. So in this sector, there are two sectors mainly, battery and supercapacitor. They are actually in net, even though they are stores electricity, they are storing in a different method. So that is the scenario over here. Before starting this, I like to introduce my organization. Just next. Yeah. See, Keltron Component Complex Limited, KCCL. That's my parent organization, is a leading manufacturer of passive electronic components and PSU under Government of Kerala, and has been operating since 1974. Since then, KCCL has grown and now is the biggest manufacturer of aluminum electrolytic capacitor in India. The company is now manufacturing aluminum electrolytic capacitor, metallized polypropylene capacitors, resistors, and crystals. Headquarters at Kannur in Kerala, with over 8 marketing office spread throughout India in all major cities. The company is a listed company with over 1,400 public shares. The factory was built up area of more than 11,000 square meters, that is nearly 14 acres of land, and skilled workmen more than 700 persons. The factory has more than 400 automatic and semi-automatic machines. The company is running on profit for the past many years, and the turnover during this 2022-23 is 94, and 2025, that is not given in this figure. 24-25 it was 105. KCCL R&D, KPP and Nambia, KER&DC, it is also KER&DC, is a DSIR, Department of Scientific and Industrial Research, Ministry Science of Technology, Government of India. That is recognized by this organization. KCCL is also ISO 9000 certified. Now ISO 9000 2015, and KCCL many products are BAS certified. KCCL has set up India's first commercial automized supercapacitor production facility. There are a lot of organizations, they already developed supercapacitor production, but this is a commercial supercapacitor production facility with a lot of automation facilities are there. And the first investment nearly 18 crores, and second investment 42 crores. Keltron was associating with the major central government R&D organization, VSSC, Center for Material for Electronic Technology, that is CMAT, and NMRL, Naval Material Research Laboratory, for the development of this technology for many years back. We have been started this collaboration with various this organization nearly from 2015 onwards. Keltron has signed MOU with ISRO at 2020 for transfer of technology developed by ISRO. So we started with the ISRO technology. Now with our R&D, existing R&D, we are improving this. Sorry, once again, power interruption.
They are able to see.
Okay. So let me start with the supercapacitor session. Before going into the circuitry application, I just want to talk about the brief manufacturing and material properties and also characterization of supercapacitor before going into the application. So first, an activated carbon-based supercapacitor constructed with a symmetric or asymmetric carbon positive and negative electrodes. Symmetric and asymmetric actually means the carbon electrode can either be that's a cathode as well as anode. They can be either in the same material composition or can be of different material composition. I'm not going detail into it because our subject is not like that. It is for application. So electrode separation by an insulating ion permeable separator and packed into a container filled with organic electrolyte, most often acetonitrile and tetraethyl fluoroborate. That's a common electrolyte. There is a number of variants, but that is a very typical electrolyte. Designed to a maximum ionic conductivity and electrode wetting, it is the combination of high surface area activated carbon electrode with extremely small charge separation that result in high capacitors. An electric double air capacitor, supercapacitor, is nothing but a high capacity capacitor with a capacitance value much higher than nominal capacitor, but lower voltage limit. That's one of the setback. Supercapacitor stores charge electrochemically. That's one of the key difference with the battery. Non-Faradic. It is known as non-Faradic. It is electrostatic. By reversible adsorption of the electrolyte onto electrochemical stable, high surface area carbon electrodes. Charge separation occurs on polarization at the electrode. Electrolyte interference. Actually, there is no oxide or dielectric in the supercapacitor. It is a interface voltage. So that is known as the charge separation, and voltage is produced by electrical double air mechanism. It's again a chemistry. I'm not going into the details. They can store 100 to 10 to 100 times more energy per unit volume mass than electrolytic capacitor. Electrolytic capacitor is one of the aluminum electrolytic capacitor, tantalum electrolytic capacitor, very compact capacitor. But supercapacitor can store even 100 times than that of the conventional capacitors. So can receive and deliver charges much faster than batteries. That is the most advantage compared to batteries. And tolerate charging discharging cycle than rechargeable batteries. The supercapacitor offers excellent power handling characteristics, and when used by themselves or in combination with batteries, provided external backup time. Then this is the an ideal supercapacitor construction. There are a lot of variations, but for a typical construction, you can represent like this. The left-hand side of the figure is a conventional capacitor, and it is compared with the activated capacitor, where conventionally there was always dielectric. Even with a chemical capacitor like electrolytic capacitor and electrolytic and tantalum, wet tantalum capacitor all contain oxide in place of separate insulators. But in the case of supercapacitor, electrical double air is the voltage forming area. And the surface of the carbon, the carbon has a lot of surface area that I will describe in the next session. That surface area is the primary factor that causes a high increase in capacitance. And also the dielectric, that's actually there is no dielectric, but it's the charge separation, double layer charge separation, that's a very, very low way. It's the order of very nanometers. And that's why when you apply this equation, C is equal to epsilon 0 epsilon or A by D, that D is extremely small, A is very high. And that's the key reason for high capacitance. In case of supercapacitor, due to the porous nature, and moreover, they are in powder form. Powder form also have porous nature as represented in that figure. Activated carbon surface area will be very high, resulting in a high capacitance. And this is some physical modeling of supercapacitor. Activated carbon is powdered to fine particles through a special process. A lot of chemical processes are there. And the particle surface area is further increased by several chemical and physical processes. 1 gram carbon could attain greater than 1,800 square meter surface area by this method. You know that for 1 gram carbon, the specific gravity of carbon is 2.2. For 1 gram carbon, when you compare the size, it is very less than 1 centimeter square. 1 cm cube. It is when you compare the area gained by this process it is nearly 50 megatimes. That much surface area is increased. The electrode capacitance of the carbon material with electrolyte is due to the electrolytic double layer capacitance and the electrical process, and to a small extent it is due to pseudo capacitance also. Even though that is not actually the main capacitance, but that exists in a very small ratio. Voltage polarization influence thickness of the electrode double layer is the order of few nanometers. That is the most important thing because D is very low. Most common electrolyte is acetonitrile, tetraethyl, ammonium tetraethyl fluoroborate. That's the apart from this, there are several other combinations, but this is one of the very common, typical type of electrolyte. The construction of electrode is like this. Carbon powder is coated on a single side of both sides of etched and passivated aluminum base foil of thickness 20 to 30 micron. Why this is etched and passivated is to enhance the adhesion of carbon material to the aluminum part. And the purity of the aluminum is nearly 5 and 99.99%. The composite electrode, so what we call as a composite, because the outer part contains carbon powder with special adhesives, and the inner center surface is aluminum metal. The composite electrode thickness ranges from 140 micron to 240 micron, depending upon the type of application. The central aluminum foil acts as an electrical and mechanical support. Due to several practical reasons, all the surface area achieved by the carbon powder processing is not utilized for the capacitor formation. Some pores are blocked and some surface area of the particles are used for bonding together during the electrode making process. So the practically obtained capacitance is, it is 100 farad per gram. It is increasing each year by a factor of 10%. That's the thing. Due to the more advanced processing technology, this capacitance per gram is increasing every time. And this is before going to our application to understand what is the supercapacitor, how effectively we can put into a circuit, we have to know what is the real characteristic of supercapacitor. So in this figure, I had given three examples, the three characterization. One is from aluminum electrolytic capacitors, and the other is film capacitors. Film capacitors are usually AC capacitors. They have a very low ESR. That's the very important thing. As well as they don't have polarization. Positive and negative can be used. And see, in the capacitor, we can put a capacitor as a capacitor only in ideal case. In all other practical case, capacitors have some ESR resistance, as well as some inductive properties, as well as some dielectric leakage properties. And this dielectric leakage is the main issue to reduce the reduction of power, that is the charge stored in the capacitor. So in the film capacitor, you can see this dielectric leakage resistance is very low. So if you charge a film capacitor, you can retain the charge for a pretty long time because it is a very low dielectric. But in the case of aluminum electrolytic capacitor, this capacitor, the resistance across parallel to the capacitor is known as dielectric leakage capacitor. That is considerable, but it is in the microampere level. And considering this inductive value, whenever a current flows, it is very low, you know that, but whenever a current flows, there is always a magnetic field. So we have to consider the inductive property of also in the case of high frequency application. That's why it is an series inductor also provided. Finally, equivalent circuit of supercapacitor is different from that of the conventional capacitor in a special way that it has an additional small capacitor which likely to be put into the parallel to the main capacitor. That we call as a deep poor capacitor. A capacitor, suppose, give me an example. If a 100 farad capacitor is we are speaking about, the D4 capacitance varies from 0.1 farad to nearly 2 farad to 3 farad, like that, because that's a 2% from maximum 2% capacitance. That's a maximum. Usually it is very low. That is a capacitor that is not available for immediate application. The main capacitor C1 is the primary capacitor. When we measure with a reasonable current density, that capacitance will always be active. Due to this very small capacitance, the surface of the electrode has a very deep pore, and ions has to travel through this deep pore to charge them. So they are not usually active, but they have a parasitical. Here, whatever the charge distributed in the main capacitor is redistributed. Pardon me, just hello. Whatever the charge stored in the main capacitor will be redistributed to the D4 capacitor to a certain extent. Depending upon the application, there are different applications. You know that some capacitors has to using as a backup and cracking systems. They need a very low ESR, but not much concerned about the D4 capacitors. Whereas in some other IoT device, this D4 capacitor is an issue. So depending upon the type of application, we will change the carbon structure. The amount of D4, we can control it by combining this electrode thickness as well as the carbon pack density thickness. If the pack density thickness is low, the D4 capacitance is low. So it's a lot of optimizations are there, but this usually have a very small effect. It is not a Faradic leakage, it is a redistribution of leakage in the case of this C, D4 capacitor. And equivalent series resistance is another important factor. Equivalent series resistance comes from all the lead connection they did. For example, 500 farad capacitor, the equivalent series resistance what we are producing is nearly of 2 to 3 milliohms. It's very low, but since it also count during fast discharge, it causes some voltage drop and it causes some energy losses. And this is the primary thing I have to talk about this supercapacitor circuit, equivalent circuit. And this is how the supercapacitor, before going to the comparison and circuit details, we have to go for this typical supercapacitor test method. See how this normal capacitors and supercapacitors are tested. Supercapacitor are not tested like ordinary capacitors. Ordinary digital capacitance meter, that is very common, like LCR meters, are designed to measure picofarad to 0.1 farad capacitor range. These instruments uses 100 kilohertz to 100 hertz to 100 kilohertz range sine wave frequency, 1 to 2 volt peak to peak. You may wonder, electrolytic capacitors are polar, then how they can melt? Because this 1 volt is not an issue. 1 volt to peak, the cathode, even though cathode is not oxidized, it can handle. So they are measured with the 1 volt peak to peak sine wave function. If the capacitance is very low, the meter will apply very high frequency, and we can also select the frequency range also. So like that, the meter actually checks the current strength, and with that current, they digitally calculate what is the capacitance value and what is the phase angle, everything. So this is a simple discussion how it is being measured. But supercapacitors, mainly EDLC capacitor with a very high density charge formation at electrode. charge density. Due to high steric hindrance of ions, supercapacitors frequency response are far from ideal. That means this capacitor has a very high concentration capacitance. Ions are packed in an extremely tight manner. So when a high frequency is applied, they won't respond. Supercapacitor is considered as an energy store device rather than capacitors. That's the most important thing. The testing instruments are designed by considering the fact that supercapacitors are high power density and low energy density storage device. That's the difference between battery and supercapacitor. Battery test system is quite analogous, but the supercapacitors are rated for high power for a short period. So the equipment is also designed like this. The equipment for testing basically a precision power supply which can operate at constant current mode as well as at constant voltage mode with voltage, current, temperature, etc. Real-time data log. Data are measured, recorded at minimum sampling rate of 100 milliseconds. So per 0.1 second data are measured. That's the minimum resolution required. All processes are controlled by custom-built software. And this is the procedure how to test the supercapacitor. Discharge the capacitor terminal capacitor. First we have to discharge the capacitor completely. We can use a very low resistance for that. Say 1 ohm, 2 ohm resistance we can use. 1 ohm is better. Put the capacitor across this resistor for a long period, maybe 1 hour is sufficient, and you can start testing this capacitor. Discharge the capacitor terminal are connected in a special jig of the tester. A special jig means jigs are made as per the configuration of the terminal. The test will provide power at constant current mode. That's one of the things. As I explained earlier, the equipment for testing can operate in both constant current and constant voltage form automatically as per the computer command. The tester will provide power at constant current mode is the charging capacity. The magnitude of charging current is determined by the nominal capacity of the capacitor. Example, 10 farad capacitor charging current is 1 ampere, whereas 1000 farad capacitor charging current is 100 ampere. It is usually taken as a 0.1 farad rated. Current is rated as a 0.1. What is the farad? 100 into 0.1. That is the current. Or 50 into 0.1. That's the current. If the farad is 50, you have to multiply it with 0.1. That's the 5 is the current density. That has to be a current applied to the capacitor for charging. Constant current mode charge will continue till the capacitor reach its rated voltage 2.7 by 3 volts. There are two types. 2.7 is also available. Also 3 volts are also available. Due to ESR, a very slight drop in voltage will happen during charging. A slight voltage when you stop the charging. A slight voltage drop will happen if the charge circuit is open. So after attaining the rated voltage, the system will automatically transform into constant voltage mode, maintaining the rated voltage for set period of set time. The system will discharge the capacitor at a constant current mode, same as charging current value. The discharge will continue till the capacitor terminal voltage will become half of the rated voltage. Example, in the case of 2.7, 1.35 is the discharge voltage. From 2.7, it will discharge to 1.35 volt. If it is 3 volt, it will discharge to 1.5 volt. The circuit will open after this point. The voltage at the capacitor terminal will rise to a certain extent due to the ESR. This open circuit voltage is also measured. This is a typical figure of a very simplified figure. Actual figure is almost like this. We can show you. This is a typical figure. Here, the left side is charging slope. That is marked as the charging current, charging slope. We know that here Q C is equal to Q by V. At a constant current, Q is equal to I into T. Current is constant. That amount of charge is determined by I into T. Where I is the charging current, discharging current, T is the time taken in seconds to reach the specified voltage. So it starts to charge the capacitor to the specified voltage. So usually the charge voltage time slope is not used for the capacitor calculation because it contains a lot of leakage current and other parameters. So instead of that, discharge voltage time slope at a constant current, discharge voltage dash voltage time slope at a constant current mode is used for capacitor calculation. That's the left, your right hand side part, and top side is the voltage holding part as described in the previous page, and this is the right side is the discharge curve path, discharge slope path. And from measuring this T2 and T3, that's the time taken to discharge the capacitor from its rated voltage to half the voltage is. Hello? Hello? Am I audible?
Yes, sir. Yes, sir. Continue.
Yes, sir. Yes.
Shall I continue?
Yes, sir.
Okay.
Okay. So this capacitance is calculated as I, that is the current what we are applying. It is a constant current into the time lapse discharge from full voltage, starting voltage to rated voltage to half the voltage. That is the time. T3 minus T2. V1 minus V2 is definitely the difference in voltage. If it is 3 volt capacitor discharged to 1.5 volt, then V1 minus V2 will be 1.5. If it 2.7 capacitor, the V1 minus V2 will be 1.35, like that. So we will get the capacitance. The computer will automatically calculate the capacitance in this case. And ESR of the capacitor is calculated using, there is a, you can see that in this figure, there is a hike in voltage. After discharge to the half the voltage, the circuit will open. So immediately the capacitor terminal voltage would be slightly increased. It will be very small in the actual figure. This is the a figure that is a notable difference I had given for understanding easily. But actually, in this actual case, it is very small due to the very low ESR characterization of the supercapacitor. So anyway, this voltage will rise, and the difference between the finally discharged volt half the voltage minus the rise voltage, it will increase to slightly from 1.5 volt discharge voltage to it may increase 1.505 volt, and that is V3 minus V2 divided by I gives the ESR of the capacitor. And this is a typical graph. Actually, this is a machine tested data. I'll also give some more details. System is also equipped with to measure various other parameters of the supercapacitor, such as leakage current, self-discharge rate, capacitor body temperature, etc. Note, this is an important thing. The capacitor are not discharged to zero voltage for this purpose. Time taken for the capacitor to discharge to half the rated voltage at a constant current mode is taken for the purpose. That's the most important thing. When a capacitor is discharged from its rated voltage to half the rated voltage, 75% of the energy stored in the capacitor will be drained. Whenever the capacitor is put into the bank, we always calculate the 75% when the bank is operating up to the after discharge up to the off voltage of the rated voltage. The bank is no more considered suitable for further power supply because it has already drained 75% because the equation is like the half CV square. So V is very important. When it is become half or 75% of the energy is drained out. And the bottom side there is a real data where you can see the very and the discharge line. You can see that discharge a very small dip in the voltage, and the voltage is slightly raised from the graph, and that is the measure of ESR, and the computer automatically calculate the ESR. As I told you, it is always in the range of milliohms. And here I'll give you some comparison of battery and supercapacitor when you're going for a circuit application, energy storage, whatever. We have to know the specific properties of capacitor. Here, a capacitor against a battery. Here we had given three data. One is supercapacitor, ordinary capacitor, and battery. And supercapacitor, fast discharge, linear or exponential voltage decay. It depends upon whether the current is drained at a constant or current is exponentially drained. If current is exponentially drained, the voltage decay is also exponential. Fast discharge, linear and exponential. With a conventional capacitor also the same behavior. Whereas battery maintain a constant voltage for a long time. That's the main advantage of battery. Supercapacitor voltage decay with current discharge, whereas battery remains almost in linear voltage, maintain a linear voltage for its ampere hour, as per its ampere hour rating. And charging actually requires milliseconds to seconds. It will charge very fast. Likewise, ordinary capacitor picoseconds to milliseconds, whereas capacitor needs minutes to hours. Battery needs to minutes to hours. And the dimension small to large. Supercapacitor compared to power, its dimensions are small. Compared to the current rating, its dimensions are more. Energy density 3 to 10 watt per kg supercapacitors, where traditional conventional capacitor it is 0.5 watts per kg. Some aluminum electronic capacitor can reach up to 0.6 watt per kg, but it's not comparable with that of a supercapacitor. But compared to battery, it is pretty low. Battery, it is 100 to 350 watt hour per kg. So battery is highly energy intensive. Compared to energy density, battery is far more better than supercapacitor. Power density. Conventional this is the standard rated, where you can find the capacitor who can discharge more rapidly, recent development. But here, as per the chart we had given, this is a nominal range. 1000 to 10,000 watt per kg is the power density. Aluminum electronic capacitor we didn't give because it is not important here. And whereas it is 200 to 600 watt per kg. This is the primary advantage. Supercapacitor is far more power density compared to that of battery. It can drain high power, a high current and voltage at a very short period of time. It can charge very fast and discharge very fast. Operating voltage 2.8 to 3 volts. That depends upon is today more than 3 volts capacitor also available. They are on R&D stage. Electrolytic normal capacitors 6 volt to 800 volts are available, whereas battery 1.2 to 4.2 volts. Life cycle is one of the most important thing. Here, supercapacitor cycle life, charge discharge. It can go up to 3 lakhs, more than 3 lakhs. Whereas battery, it is nearly 2000 cycles. Of course, there are batteries which can stand more cycles. Recent development are going in such a way that they are trying to increase the battery life further to 10,000 cycles, even more. Working temperature minus 40 to 70 degrees centigrade, whereas the normal capacitor working temperature is much more wider than supercapacitor, but still supercapacitor has a higher working temperature range compared to battery, especially in lower temperature range. The working is far more better than this data sheet itself. And this is a definition. A battery is an electrochemical storage device that store energy through chemical reaction, redox reaction, and release its as an electrical energy. Supercapacitor, a supercapacitor ultracapacitor, is electrochemical energy storage device that store energy electrostatically, electrical double layer, without bulk chemical reaction. That is the simple comparison. The storage principle, chemical energy, electrostatic mainly, reaction type, bulk chemical reaction in the case of battery, surface charge accumulation. Even though deep pores are there, main capacitance from surface charge accumulation. Reversibility, limited battery is Faraday. It is not 100% reversibility. That's the cycle limitation for the charge discharge cycle limitation of battery. Compared to battery, supercapacitor is highly reversible. Energy density, as we say, 100 to 300 watts lithium ions. Supercapacitor 3 to 10 watts only. Power density 200 to 600 watt per kg, whereas that's of supercapacitor more than 10,000 watts per kg. Charging time minutes to hours. In the case of battery, supercapacitor can be charged within seconds. Discharging time minutes to hours, seconds also. That's why we are able to get high power pulse. Fast charging will deteriorate the battery, but not usually supercapacitor. Fast discharge. Very high discharge sometimes can cause a terminal burn as well as damage of the other circuitry. Cycle life battery is as I say, advanced cycle life up to 10,000 is possible, but in the case of supercapacitor, it is more than 3 lakhs. Efficiency, battery efficiency is 85 to 95%. Charging and discharging. Efficiency decreases at high current. Supercapacitor round trip efficiency is 95 to 98% because the charge is stored electrostatically and the ESR is extremely low. Efficiency remains same for a wide range of charging and discharging current. That's an advantage of supercapacitor. And voltage characterization, that's the nearly constant, whereas supercapacitor battery nearly constant, whereas in the case of supercapacitor nearly linear decrease for a given discharge current. Requires bidirectional DC devices in some cases. Cutoff, yes, cutoff means if the voltage for whatever the bank, supercapacitor or battery, we only have to cut off, we need to cut off the voltage. If after a particular level of voltage, it will not function properly. It will start to leak. They are applicable to battery as well as supercapacitor. A maximum voltage that can be applied to the terminal is important in the case of supercapacitor as well as important that's in the case of battery. And safety, battery, fire risk, there are some fire risks are there. Where in supercapacitor, inside the capacitor there is no fire risk. But if you connect the capacitor terminal, so say for example 1000 farad capacitor terminal, if it is short circuited, the wires will ignite. So that's all. But inside the capacitor, it is made in such a way that it don't usually ignite. So the inside the device is much more safer. Thermal reversibility possible. Thermal runaway. In the case of battery, it is possible, but not usually observed with the supercapacitor. Our charge damage considerable, but to a certain extent, supercapacitor can regain its parameters after 1 or 2 days, because the pores, whatever filled with the gases, if it is not exploded, it will regain. So the capacitor to a certain extent will come back, slightly reversible. But batteries are very dangerous with the high voltage. It is not much reversible. Environmental risk, electrolyte leakage, that can occur also with the capacitor, but to a very low extent. Self-discharge. Battery, that's the most important here. This is the main disadvantage with the setback with the supercapacitor. Battery has a very low self-discharge because it produces power. Supercapacitor is not producing power, it is storing the power. So it produces power by the electrochemical means, even though there is a discharge over there. So battery load self-discharge, when you measure the voltage of the battery, 2 to 5% per month is only possible with a good battery. Whereas supercapacitor high self-discharge, 5 to 20% per day. But the technologies are evolving in such a way that each time we are bringing down the leakage of the self-discharge of the faradic discharge of the supercapacitor as low as possible. 30 years before, it is very high. Now it is very low. Maintenance. Battery requires periodic maintenance, especially lead acid battery, but lithium-ion tri-batteries not requires periodic maintenance, but it has to be changed after some period of operations. Especially in automobiles where high current densities are used. Supercapacitor maintenance-free, long service life. Usually the service life what the customers expected from supercapacitor is more than 10 years. If it has been operating at a nominal condition. And this cost, battery, it is a cost per watt hour. Battery it is low, but supercapacitor is high. Cost per cycle, that it is high because the cycle that we can use for battery it is not much high. So the cycle use it is high. Whereas even though initial investment are there, the supercapacitor is a very low cycle cost per cycle. Lifetime cost moderate, whereas in the case of supercapacitor it is still low. Application. Battery application, you know that already. Everyone knows. It is widely used in all electrical and renewable area. Whereas supercapacitor application I am pointing out. Regenerative braking is one of the energy recovering system where high current power pulses coming. So supercapacitor has some role to manage this high power burst. Frequent start-stop systems like trams and other things where it has to stop and start, an industrial floor transportation system inside the industrial floor. These equipments, this transporting unit has to stop and start, stop, start, stop, start. In that case, it is better to go with the supercapacitor rather than going with the battery. Some of the manufacturing lines they use only supercapacitor in place of battery. Power buffering, as we told. IoT system. In IoT system, actually, there is no requirement of high power burst. What they request is a very high cycle life. So here they are using the charge recharge cycle life in the supercapacitor is considerably higher when you compare with that of the battery. So in IoT sector, they want this, they are taking this advantage rather than high current, high power application property. Spot welding, another area where you can replace massive transformers and other things. We can use supercapacitor bag for spot welding. In many of the car manufacturing spot welding area, some of them, they are using supercapacitor in place of conventional transformers and high current devices. High pulse power handling sector. As I told you, high pulse power handling sector is one is from the regeneration, and another is from this spot welding. Likewise, lot of areas are there. Memory backup. Memory backup in smart energy meters and other things. Memory backup, they will be using primary cell or primary cell earlier or secondary cell in some case. This will totally replaced. In many cases, it is being replaced by supercapacitor with smaller value. Again, high current property and high power property is not used. Its cycle life is important here. And a hybrid, what is a hybrid supercapacitor? See, there are research in which the battery itself is transformed to supercapacitor. The battery have properties like battery as well as supercapacitor. That's a Faraday charge storage as well as contained electrostatic storage. And this is not like that, but we mentioned here is hybrid battery supercapacitor is battery one side and supercapacitor another side. So they can handle energy demand. Supercapacitor handle peak power demand, peak power, benefit improved battery life. See, one of the typical example in our car, domestic car, we are mostly using 42Ah battery. During the cranking, engine starting, that means cranking, the peak current is nearly up to 200 to 300 ampere, instantaneous current. And that's not good for the battery. If supercapacitor is being connected in parallel, it can, the voltage of the battery also come down from 12.8 volt to nearly to 8 volts in some cases. So that drop, supercapacitor can prevent that much of drop. It can provide peak power so that the life of the battery can be considerably improved. It is without a DC to DC converter, nothing like that. Simply connecting supercapacitor bank to the battery can improve the life of the, in some cases like cranking. High system efficiency. Summary table, this is a total summary of battery to supercapacitor. Energy density high, supercapacitor low, power density moderate, supercapacitor is high, charge time long, short, supercapacitor, cycle life, battery lower, supercapacitor very high, self-discharge low, fast discharge. That's the key disadvantage of the main disadvantage of the supercapacitor, but it is coming in a lower extent due to the intense research in this field. Efficiency good. In the case of battery itself, compared to our existing internal combustion engine, petrol engine produce only 30% efficiency, diesel engine produce maximum 50% efficiency, but battery can produce very high efficiency battery. Motor itself is rated for more than 90. BLDC motors can work more than 90%. So battery can provide power nearly to 90% efficiency. So they are very good. But supercapacitor is still better because they had got extremely low ESR. And the charges are stored electrostatically. So that is efficiency is excellent in the case of supercapacitor. Only the small amount of discharge will happen. And balancing circuit not required for the battery usually. Required for supercapacitor bank for high reliability. We can one can design a supercapacitor in series, say 10 numbers, 20 numbers in series, matching the capacitance very precisely. A manufacturer can do that. So the voltage shared in the bank is equal to all capacitors. But this is not a very good practice because if any capacitor have some more deterioration, its capacitance become slightly lower, then the voltage on that capacitor will be naturally high. So that increases the deterioration. So it is better to go for a balancing circuit for a high reliability application. But for nominal application, say for 8, we had been started, we had manufactured trial production and tested jump starters. This jump starter uses 500 farad supercapacitor, 5 numbers in series, and there is only a resistor balancing circuit is enough for such thing because the numbers are very low, and as a manufacturer we can control the number capacitance value. But for a very high reliability, it is better to go for a balancing circuit. Even if the capacitor is number of capacitors are too much in the circuit, balancing circuit is a very high requirement. That's one of the disadvantages of the supercapacitor. It has an additional cost. Safety, in the case of battery, there are some risks. Especially we pack more and more energy in very small volume. There are technology to overcome this risk, but as well as there is a risk associated with battery. There are some incidents. The batteries are catching fire, but the research are going in such a way that they can rectify it. But still, the battery has more compact energy, so the fire risks are there. For supercapacitor, as I told you earlier, inside the supercapacitor, the probability of catching fire is very low. But due to the extreme discharge condition, if you are not careful with the supercapacitor circuitry, that could have chances of fire. Conclusion: this is batteries are suitable for long-term energy storage, whereas supercapacitors are suitable for short-term high-power delivery. A hybrid system combined with both provide optimal performance in modern energy storage applications. Okay, and now we go for few examples, and after that we go for the practical equipments. We will demonstrate what is the practical equipment already in use. This is a hypothetical case. This is used everywhere, not everywhere, in some areas. But I'll give you the example here. So typical regenerative braking. This is a case of elevator. Regenerative braking scenario during descent. So we can utilize the energy. Suppose this is a hospital. Everybody going up will be coming down. So the total overall potential energy will be same. So in the normal case, we have to lift the people to the top floor and also have to apply the brake. So the energy will be wasted. So instead of that, if you regeneratively harvest the power, we can save a lot of energy. That's the scenario over here. A typical regenerative braking with a full load condition, energy losses during energy conversion is not accounted properly, only for representation. Typical 10% elevator, man with full load, 1,800 kg, considering the cabin counterweight. It can be the weight of people only, 800 kg. Downward moving speed, let's assume it's 2 meters per second, it is a nominal speed. And BLDC motor capacity, suppose the system is operating with a BLDC motor capacity 8 kW, 48 BDC. For a 10-story building height, nearly 33 meters. So we can account 30-meter potential. So maximum potential energy due to this 10 persons at 10 story is 800 into 9.8 into 30. That is 2,35,200 joules. Considering some losses, we can account. We can round up to 22,000. Sorry, 2,22,000 joules. That's 220 kilojoules. So our input power is 220 kilojoules. Instead of breaking, we can produce it, we can regeneratively break it, and the power produced during the regeneration we can use for the charging of the supercapacitor. That's the concept here. Average time to descend from top to ground floor is 16 seconds. Average power regenerated is nearly 2,20,000 divided by 16 is the 13.75 kilowatts. Regenerated current is 48 VDC. See, since we are using 48 VDC, it would be 286.45 ampere. 286.45 ampere. So our bank should be able to handle this much amount of current at 48 volts. Supercapacitor bank, what we proposed here is 300 farad, 48 DC by 14 numbers of 3000 farad, 2.7 or 3 volt capacitor. Individual unit can be arranged like this. That 20 nodes in series, two such series connections can be parallel, so that the combined bank output is 300 farad, 48 volt. Storable energy of this bank is 48 volts. At 48 volts is using conventional equation. Again, we had put 0.75. That is the capacitor is discharged only of the rated voltage. You can consider from 48 to 24 volt. That's why it's 0.75 comes 0.75 into 300 into 48 square divided by 2. That is again 2,59,200 joules. Regenerated energy as per theoretical energy is nearly 220 kilojoules, and this is 250 kilojoules. So our bank can safely handle the power regenerated during descent. The bank can handle 600 because as per the capacitor configuration, the bank can handle 600 as per the specification. 600 ampere of current as per the specification is steady current. Regenerated current is, as we calculated earlier, it is only 286.45. So it's also within safe limit. So this is a maximum steady current. That's only for indication given for this 8 kilowatt BLDC motor. Conclusion: 600 farad 48 VDC supercapacitor bank with bidirectional DC to DC converter is ideal for regenerative power harvesting. So we, even though there are losses, we can save up to 40% power, 30 to 40% power. It is already done in several areas. So that's a very promising area where you can use supercapacitor. Initial investment are a little bit higher due to the capacity, because capacitor slightly cost higher. But system, as the cycle life is concerned, we don't need to worry about the maintenance of the system. So once the cycle life, when you calculate, the overall investment is very good. So this is a promising area where we can use the supercapacitor without any battery in parallel. And this is a EVM regenerating braking scenario. EVM actually that is a you know that now we are in the EVM period, and earlier EVMs were using 24, 48 VDC, BLDC motors. Now this is totally changed. We are using higher voltage battery. So in this sector now the situation is not much promising. That according to the calculation, let's go for the calculation. Rapid braking condition, no loss of energy is accounted only for representation again. Car with passengers 1,200. That's a typical small car weighs with passenger. Car weighs is nearly 800 kg. Passengers full, you can assume it is 1,200 kg. Traveling, suppose we are traveling in Bangalore Mysore highway, 100 km/h is a very nominal speed. It is 27.8 meters per second. And if somebody brakes from 100 kilometer to 40 kilometer per hour, the potential, the kinetic energy difference is 3,89,646 joules. So that's the burst of energy. In this, if this is done in 3 seconds, deceleration from this speed, 100 kilometer, 40 kilometers, if it is done in 3 seconds, the G forces is 0.57 G. That's okay, pretty good G force, but in case of emergency, that level of braking would be there. Average regenerated power here is 3,89,000 divided by 3, 1,29,882 watts. That's nearly, you can say, 130 kilowatt is the regenerative power in 3 seconds. A typical 300 farad 3 volt capacitor can hold 10,000 joules. 40 numbers of such capacitor can is okay for harvesting energy as per the, because it is a 4 lakh joules you can obtain with 40 capacitors. However, the working voltage is limited. We can use continuous supercapacitor in series and rate this unit for 50 volts safely. Can go rate for 60 volts, but better to go for 50 volts safely. This such unit parallel form of capacitor bank for 50 farad, 3 such unit for 50 farad 50 volt. That's our bank capacity. Suppose this is the for 50 volt 50 volt farad 50 volt bank capacity. Energy capacity of this bank is nearly 4 lakhs something joules. Is sufficient to harvest the generated by braking energy. The current from the regenerative braking reach up to 2,600 ampere, because we have to step down the current voltage. Nowadays the EVM motors are running at a very high voltage, not at a 50 voltage. LDC more, because to reduce the to increase the efficiency. So we have to bring down the voltage, and when we bring down the voltage, the current definitely increases, and it is 2,600 amperes. As per the capacitor bank, 3000 farad axial capacity, this peak current for a few seconds is okay. However, it is difficult to design a DC-DC bidirectional converter to match with the EV's motor generator input and output. So every time they have to change this current, not to charge the capacitor. The regenerative current produced for is, suppose what is the situation, direct charging situation with battery. We check that the regenerative current produced at 400 volt DC. That is 130, that's our power, 130 kilojoules divided by 400, that's only 325 ampere. In place of 6,500 ampere, if you step down to very low voltage. Here, standard EV motor powers 50 to 100 kW, 75 kW for calculation. These usually they ranges from 50 to 100 kilowatt. Standard EV, but we for calculation purpose we can take it as 75 kW for calculation. Therefore, the current consumption is nearly 187.5 peak current, maximum current. Typical 400 volt EV charging current is 16 to 48 ampere. That is low, of course, but DC fast charging can hit to 150 to 300 amp. Nowadays, they can charge up to that. Some Tesla model even charge for 625, but the voltage is still higher. Conclusion: in this method, the technology of the present EV battery itself allows to manage this pulse charging current to a certain extent, because production is 325 ampere maximum, and normally they can handle 187.5 ampere in working, and charging current can go up to 300 ampere. So it is not much different. So this is a very emergency casing, braking casing. Normal regenerative braking is still lower. The current produced would be still lower. So they can easily handle the recharge the battery itself. So supercapacitor is an option only here. So this is our Keltron product. This is a product with a supercapacitor jump starter. A jump starter, we will describe it. Keltron introduced an inverter solution for the. There are some jump starters abroad also. We can also import these starters, but we in-house we have developed this jump starter for our as a part of our capacitor utility product. For starting our vehicle when the battery is dead or discharged. The supercapacitor powered jump starter is compact and convenient device designed quickly to resolve the frustration of car that won't start due to dead battery. Simply connect the jump starter to the battery terminal and it will provide a necessary power to start your vehicle, allowing you to drive safely to the nearest service station. A jump starter uses advanced supercapacitor technology to store and deliver power, enabling vehicle start even with weak 12-volt batteries. That usually this capacitor, the battery cranking for starting the vehicle, you need a very high power. So after that, once the vehicle is started, we can use the generator will produce, and the power required by the battery is very low. So only for cranking purpose, the power required. So that's what the super importance of supercapacitor comes to a major role. A jump starter, also called boost, is produced of starting motor vehicle, most commonly car, trucks, that has been discharged. That is a discharge battery. A temporary connection is made to the external power source called jump starter. The external supply of the electric provides the power needed to crank the engine. Once the vehicle had been started, its normal charging system will recharge. So the auxiliary source jump starter can be removed. If the vehicle charging system is functioning, leveling the engine running will restore the charge of the battery. Motorist may carry the handy jump starter for use in case of accidental discharge of the vehicle battery. For example, headlight, interior lights, ignition switch left on when the engine is not. I have the same situation when I once forgot to switch off my headlight when parked in my garage. The jump starter is a batteryless, use only supercapacitor. Specification. Output voltage 12 volts, suitable for vehicles with 12-volt batteries including 32Ah batteries. Peak current 600 ampere, adequate for jump starting smaller currents with 32Ah batteries. Working storage temperature -40 to +65 degrees. Input voltage 12 volt, 6 volt, 12 volts is 3 minutes, 6 volt is 20 minutes, 5 volts 30 minutes. There are DC to DC converter which regulate the power. Weight 1 kg, size 26, length 9.3 width, 5.3 height in centimeter. Application for household purpose, automobiles, workshop, including small car. Supercapacitor base, no internal batteries required. No pre-charging requires, ready for immediate use. It can durable lifespan 10 years or reliable performance. Engine compatibility supports gasoline engine up to 7 liters and diesel engine up to 4 liters. It uses only 500 farad. If we go for above 500 vehicle, we can go for even more heavy equipments, heavy vehicle starting. This is the first model. And also one more important thing I forgot to tell you, because it has a DC to DC converter that can charge from a almost drained battery. Even though the car battery is drained to 6 volt, it can charge. It can pick up the residual current, power inside the battery and charge the supercapacitor. Because supercapacitor need less. Supercapacitor is a high power devices but at the same time it's a energy device. Energy is low. There's high power density devices, low energy density devices. So the charging inside even with the 7 to 6 volt is sufficient to charge the supercapacitor to the 12 volt, 12.8 volts and restart the vehicle. That's an option with the supercapacitor jump starter. Whereas lithium ion jump starter, it has to be charged separately. we cannot use a dead battery to, not a dead battery. Dead battery is not possible with supercapacitor. Sir. We cannot use a dead battery or low battery to charge a lithium system because it needs lot of power, lot of Q current to get it fully charged. And another, this is for our internal use only. It's a supercapacitor powered trolley. Keltron introduces this is a system. This is a hybrid system. Significantly boosts the trolley's energy efficiency by allowing stress and battery, which turn extended lifespan and reduces efficiency balancing. This is used for our domestic transportation, such as they don't need a specialized person to drive the system. Only handle is there. There is a small accelerometer is over there. They can anyone can easily handle. Perfect for industrial setting like waterhouse and factories as well as commercial environments such as airport living. This is only a trial prototype mode. This innovative trolley processes more responsive durable energy efficiency during material handling. And this dimension is 1.1 meter, 0.7 meter. The unit weight is 82 kg. Input supply voltage 230. Weight carrying capacity 400 kg. Charging time 2 hours. Because it is a hybrid system. It also contains a battery. Operating time 7 hours, one single charge. Inbuilt AC charger 230 volt AC and 58 volt DC. We limited the current. Supercapacitor bag 25 farad 54 volt. Battery capacity 15 H 54 volt. With these two configuration, we can operate it because when it climbing in a space, when you use it outside, supercapacitor deliver more power. So that's the method. That's the scenario regarding supercapacitor, and I think it's time is already there. Yeah, I don't have much time to introduce our capacitor production facility over here. I think only good. How much time left?
50 minutes.
I think for a quick plans, I can go through our capacitor specification as well as plus.
Just back it. Is it viewable?
Is this capacitor data sheet is viewable? Hello?
First page
Yes, sir.
is showing, sir. Powering the future, that page.
Yeah, power the fuse. Yes. Sir, this is our browser. We can go for a quick reference. And,
ഇവിടെ ക്ലിക്ക് ചെയ്തിട്ട് ക്ലിക്ക് ചെയ്ത് പ്രസ് ചെയ്താൽ ഒത്തിരി ക്ലിക്ക് ചെയ്ത് പ്രസ് ചെയ്ത് ഇവിടെ ക്ലിക്ക് ചെയ്തിട്ട് പ്രസ് ചെയ്ത് നോക്കി ഇവിടെ ക്ലിക്ക് ചെയ്തിട്ട് പ്രസ് അല്ലെങ്കിൽ സ്ക്രോൾ ചെയ്യേണ്ടി വരും ഇവിടെ പ്രസ് ചെയ്തിട്ട്
time is already removed. ഇത് വരുന്നില്ലല്ലോ. Since our time is nearly over, I just want to conclude, sir. And thank you everyone to listen patiently. And any comments regarding this is highly welcome.
Okay, participants, if you have anything to discuss, please make use of the time.
Sir, could you please? Hello, sir. Sir, could you please,
Yes.
tell about the cost of a 500 volt, 500 microfarad, 500 farad, 2.5 volt capacitor?
It cost nowadays our cost the production voltage is not too much, but it is cost nearly 600 rupees, 700 600 rupees. It will come down to our target is to bring it down within a couple of months to nearly to 400 300 400 range. Since the volume of production we had started the production not in a full swing. When it comes to the full swing of production, when the production volume increases, you can expect much lower cost. Now it is nearly 700 rupees.
Sir, what is the minimum rating of capacitor available?
We can have okay. There are 1 farad from 1 farad is available, but as per the Keltron range, we started from 5 farad. Seriously connecting to such configuration to 2.5 farad, 5.4 volt, we are providing for IoT sectors. 5 farad is the minimum range, but soon we can go down to 3 farad also.
Okay, sir, thank you.
5 to 500 is our present range. We are coming down, we will certainly come down below 5 and above 500 farad.
Anybody else? Okay, so
Yes, sir, can we conclude now?
yes, sir, we can conclude. So, thank you, Sudhir sir, for the excellent session on supercapacitors as an intermediate energy storage device. And your practical insight from industry, especially on design, material, and real-world implementation, were extremely valuable and gave our participants a clear application-oriented perspective. So, on behalf of the organizing team, we sincerely thank you for your time and knowledge sharing. Thank you, sir. Thank you very much.
Thank you very much, sir. Thank you, all of you.
Okay, sir. Thank you.
Stop.
So, dear participant, we will soon start our second session.